10 o'clock. Good morning, guys. Thank you for joining another edition of the Long Coffee Break. My name is Joshua Like, sales engineer here in Grand Junction. Today we're going to be discussing the evolution of control valves. With me today, we are fortunate enough to have Jerry Martin, National Sales Manager of Griswold Control, to discuss this topic. So, Jerry, when you're ready.
Great. Thanks, Josh. Thank you, everybody, for your time. I really appreciate it. I'm going to quickly cover the evolution of control valves over the past half century or so. Energy was typically free. Believe it or not, comfort was not a priority. We weren't doing a whole lot of chilling. We weren't doing a whole lot of cooling. Mostly we were moving water for heating. Temperature control valves were an afterthought. If we did have temperature control valves, they were on off and more than likely pneumatically controlled. The balancing practice at the time was reverse piping. The image here is actually of a 40-story skyscraper in New York City. So just throwing that out there. But having this in this scenario, we had a lot of issues. And were there any benefits? Yeah, sure. There were some benefits. We got heating in the coldest times of the year. But the problem with it is that we had constant speed pumps. We were constantly pumping water. And was the water making to the further reaches of the system? Who knows? If you were able to cheat death, maybe you only lost your toes. If you were able to get heating and hopefully you weren't too close to the pump, you weren't driven nuts by the constant water velocity noise in the piping. Not only did we have issues there, equipment malfunction was very common. Pipe erosion was extremely common. So they were constantly working on these systems trying to fix them. So therefore, we go into the evolution of the control valves. Temperature control valves started becoming more and more popular to where we're shutting off zones or shutting off coils when there wasn't anyone in the space. But it still didn't help us in a lot of the issues of balancing the system, so we were able to push the water where we needed to go. Years after the introduction of really temperature control valves, the introduction of balancing valves were brought in the mid 1900s, 1950, 1960. Griswold Controls actually introduced the first balancing valves as an automatic flow limiting valve to help push water throughout the building to address hot and cold, hot spot areas. And at the time we started doing cooling, cold spot, hot spot, cold spot areas. Okay. So there was a lot of smart people out there that realized the benefit of differential pressure controlling an orifice that would hold back the flow from allowing it to overflow a coil and diminish the performance of the coil. So automatic flow limiting valves were added. Okay. So then, those guys like that, right? Okay. Pressure independent control valves came into play because they really like the idea of the automatic flow limiting valve controlling the flow. Well, we can do the same thing with differential pressure, kind of same premise. Where we're at now, valves are getting smarter. We're able to pick up data. We're able to control valves in different manners, whether it's going to be delta P or delta T. From here, where are we going to go? It's almost like we're reverting back a step to where, we're really figuring out how to control the system really well. Maybe we need to start looking at being more compact, more versatile, and easy and inexpensive. So that's kind of where we're headed is what, how the layout's looking. So let's talk about what DP, GPM, and CV, what's the flow? What does it really mean? The thing about GPM and CV is they are absolutely equivalent at 1 PSID. And remember, we must have 1 PSID differential across the valve to have flow. So as that differential increases, so does velocity, so does flow. So you can imagine if we have a CV of 7.5 at 1 PSID, I have 7.5 GPM. Okay, per my formula, GPM equals CV times the square root of delta P. What's the square root of 1 PSI? 1. Okay, so therefore 7.5 is my GPM and my flow. However, if if that differential pressure increases due to temperature control valves closing throughout the building, say I go up to 4 psid, okay, what's my flow now? If I have 7.5 CV and I have 4 psid, 7.5 times 2 is 15 GPM. Okay, have I impacted the performing or the cooling performance or heating performance of my terminal unit or my coil? You sure have. Okay, and what does that do? That's going to impact your plant. It's going to impact tenant comfort. It may even increase noise. So you're creating a lot of issues. And remember, our temperature control valves, our pressure dependent temperature control valves, they are, they're subject to flow changes when differential pressures change. So that will cause the valve to hunt to find a new set point. If my differential pressure goes up, my GPM goes up. If the differential pressure goes down, GPM goes down. Okay. So with that, the delta T is inverse to that. So if my GPM and DP have gone up, my delta T is going to go down because I'm moving the water quickly through the system. Okay. Or quicker through the coil. I'm sorry. That impacts, like I said, our coil performance, our delta T back at the plant. Our valve's going to wear out sooner because it's hunting to try and find that new set point. Okay. The chart here kind of gives you an idea, a little bit, a different visual here. Pressure increases, flow increases. Okay. Each one of these colored lines represents a different modulated state in that valve. And the thing about temperature control valves, they are dependent upon pressure in the system. So they are going to be responding constantly to differential pressure changes in the system. So talked about bringing automatic valves into the system to help move the flow throughout the system to make sure people are getting the heating and cooling they expect. We want to give them comfort. Okay. Well, we talked about automatic flow limiting valve being the first one introduced. Okay. That was great. It worked out, pushed water where it needed to be, but it added cost. Okay. So then they came out with a manual balancing valve. Well, the manual balancing valve is really kind of cool because it's adjustable, but it's really not cool because it's adjustable. The reason why I say that is because you get a lot of people that are going through that building that don't have a clue why that handle's at, 45 degrees from being fully open or fully closed, or 15 degrees from being fully open, fully closed. He's going to come and take that and open that sucker wide open and going to knock that building out of balance. So now you're going to be spending more money to bring that valve into balance so the building can come back into balance. So let's talk about tab labor, test and balance labor. You're going to have excessive test and balance labor on your manual balancing valve that will eliminate all the savings you're expecting to get because you went away from automatic flow limiting. Because remember, we have to adjust those things constantly because we're changing the flow profile going through every valve in the system. Where an automatic flow limiting valve, we just have to go verify flow. Hey, do I have my differential I need to push flow through here? Great, I'm done. Okay, so it's really kind of a hit or miss thing on manual balancing. Okay, so also talked about pressure independent control valves, another evolution. Okay, what we want to do is we want to have the ability to match the flow to the load. We want to get our coil performing, where we got it designed, and we want it to have it at all modulated points. Remember, on our buildings today, they only operate at design condition maybe 4% of the time. The rest of the time, the balancing valves are not in play. We're dependent upon that temperature control valve to give us the set point control that we're looking for to match the flow to the load. That doesn't happen because differential pressure changes. So with a pressure independent control valve, what we do is we do something very similar to an automatic flow limiting valve to where we control an orifice with differential pressure. So this valve has got two orifices in it. We got the primary orifice, which is controlled by the BMS and your actuator. And we have a secondary orifice, which is controlled by delta P being applied to the valve. So if the delta P on the right-hand side of the valve, that blue arrow, if that changes, if that goes up at all, that's communicated up to the top of a piston, which minimizes the secondary orifice. So there we go. Flow's going up. What do I want to do? I need a smaller hole. Okay. I want to hold that water back, and I don't want it flowing through the system so quickly or through my coil so quickly to diminish my delta T. Smart valve. Okay. We talked about this, and you guys may be hearing about this from different manufacturers. A smart valve is basically a BTU meter with a control aspect. Okay. We're going to be able to pick up data, delta T, delta P. All right. You want to know what? I know delta P. I can convert that to GPM. Boy, I know that. What can I do? I can solve for BTU per hour. So now your owner can trend that data, and he can verify that that air handling unit or that zone or whatever it is functioning as efficiently as the day he turned it on 5 years later. You know, maybe 5 years later, he's saying, okay, I want to make sure this works as good as it did, you know, when I installed it or when it was commissioned. So lots of benefits with this stuff. And the neat thing about this valve is that it can run as a differential pressure, or, you know, can run off a differential pressure like a typical PIC V, or it can run off a delta T target. So say, for instance, I have an air handler that's controlling a lab temperature. I can target a specific delta T, and the valve will control to that delta T only. Okay. It'll give me a 20-degree delta T to make sure that this room doesn't change state or change its temperature. So really that's kind of the direction where we've gone, but have we gone too far? So, you know, I kind of said we're reverting back to almost cheaper, easy, I shouldn't say cheaper, inexpensive, easy to install real estate. Real estate is prime now. I grabbed an image of a horizontal fan coil, 4-pipe fan coil. Boy, there's a lot of stuff crammed into that compartment. With this new valve, we can either go temperature control or we can do flow and temperature control. But what's neat about this, it looks like a piece of pipe. Okay, there's no actuator that sits on top of this valve. The actuator is internal. The water flow actually goes around the actuator. So that means this thing can be mounted in any position. The little control panel that you see in the left-hand image, that can be mounted 20 feet away if you want, or you can mount it right on the pipe. So it's really kind of unique. I'm going to say cutting edge technology. There's no ball inside of this valve. We're using a ceramic disc to give us a characterization we want so that we can get a good equal percentage characteristic. So this is the new and latest and greatest coming out of Griswold Controls. I really appreciate your guys' time. Last slide here. I just want to make sure everyone realizes that Griswold truly is a one-stop shop. We can do everything from just basic balancing valve coil packages. We've been manufacturing temperature control valves for many, many years, pressure independent control valves. We've got BTU meters. We have lead-free valves for domestic water, potable water. So I really, again, appreciate your time. And I thank you. And we look forward to working with you. Josh, it's all you, man.
Thank you, Jerry. It's pretty cool to look at the future of what we got going on for sure. Get that going. And then please join us next week for our next coffee break, where Jeff McBride will be discussing electrification, decentralized ventilation, 100% outside air, energy efficiency, and healthy buildings. Thank you for joining us.